Okay, let's continue our review of main concepts and topics. I talked about this, supervised learning. And again, remember, when you want to use supervised learning, this is the required part. So if, for example, for your project, the data is not labeled, remember, if the data is not labeled, you cannot use supervised learning. So whatever you want to predict right here, it should be available in the training stage to train your machine learning. If this is not available, it means that you are not able to use supervised learning, and probably you need to use unsupervised learning. So remember that. All right, two basic approaches of supervised learning that we talked about last semester are classification and regression. Okay, so this is very important to understand the difference between these two, and then it can you need to know that so that you select the correct algorithm for your problem. In classification, we predict a discrete valued output. Remember that. The labels are discrete or categorical. It can be binary or non-binary, doesn't matter. So binary samples like, for example, rainy, sunny, or spam, not spam. These are binary samples. It can be non-binary like rainy, cloudy, sunny, or for iris flower, Setosa virginica versicolor, as you remember. But still, these are categories, these are groups. This is not a number, okay? Remember that. So this part can be a little confusing. You can assign a number to each group. So for example, you can assign 0 to this guy, and 1 to this, and 2 to this, okay? And train your machine learning based on 0, 1, 2, and it predicts 0, 1, 2 for you, okay? This is your label. This is a number, right? But in fact, this number represents a group. So this 1 represents sunny. This is not a real number. You don't want to predict a value. You want to predict a group. You can show this, you can name this group, for example, group 0 or group 1 or group 2, but still you want to predict a group, a category, a discrete value. However, in regression, you want to predict a continuous valued output for your observation. You want to predict a meaningful number. For example, you want to predict the housing price, which is a number, it's a continuous number. Or you want to predict a stock market, which has a continuous value, and the value of that is a meaningful number. Okay, so this is important to remember. So last semester we learned that to check how well a classifier works, we use some parameters like accuracy, for example, or some metrics that we learned later, such as a true positive rate versus false positive rate. And we learned, for example, the ROC curve. You remember ROC curve was the curve that shows how well you predict something, and the area under the ROC curve, area under the ROC curve, or area under curve, or AUC. So these are the factors, some metrics that we can use to evaluate the performance of our classifier, to see how well it classified the data. And for regression, we don't have such a thing, because we don't predict. So accuracy is the number of samples you correctly classified versus the total number of samples. So if accuracy is, for example, 75%, it means that you correctly classified 75% of your samples. So out of 100 samples, you correctly classified 75 of them. This is what accuracy means. But we don't have such a thing for regression. Instead, for regression, we define some kind of closeness when comparing the prediction with true values. So for example, we calculate error, the difference between your prediction and the actual prediction, the difference between your prediction, for example, for value of the house and the actual value of the house. There is a difference. You use that difference to, or error, to evaluate your model, and there are different metrics for that. The most important popular one is RMSE, root mean square error. Okay, so in fact this is error that so the differences for predicting the value of each house. We square them to make it positive, because sometimes you make positive error, sometimes you make negative error, sometimes you predict higher than actual value, sometimes you predict less than actual value. Both of them are errors. If we add them up, they will cancel each other, because some of them are negative, some of them are positive. To avoid that, we squared them first to make all of them positive, or absolute value in some cases, and then mean means average, and then a square root to return this back. Okay, so this RMSE, or another metric MAE, which is mean absolute error. Okay, so this is absolute value rather than a square. So these are some metrics that you use to evaluate performance of your regression. So these are for regression. Remember that. So I noticed that some of you in your projects last semester, you had a regression model, and you developed a regression model and trained a regression model, but then you provided, for example, ROC curve to evaluate the regression. So this is not a correct way. So this is how we evaluate the performance of our regression model. All right. So classification, of course, your samples are categorical, and this is your classifier to classify samples. As I mentioned, it can be non-binary. You can have many labels. You can have like 10 different labels, or you can have 100 different labels, but still they are not numbers, they are groups. 100 different categorical labels. In regression, your value, your output, something that you want to predict, is continuous valued. And again, when you compare this graph to this graph, you should remember it can be a little confusing. So look, and this graph is different from this one. In this one, I have features here. This is my feature 1, this is my feature 2, okay? And the label is the color of this samples. But in this graph, only this one is feature, okay? And this is the target, the output that I want to predict. Okay, so this is, I have one feature only here, one feature, and this is the target. But in this case, I have two features. This is feature 1, this is feature 2, and the color, this label, this is the output that I want to predict. Remember that. So I have training data in regression. Linear regression is the simplest, of course, model. In many cases, we really don't use linear regression because usually the data is not linear. The data does not have linear pattern, but still it works. But a very important thing to remember, I mentioned that last semester, and I want to emphasize that again. Linear regression, right, this is a very simple, but it's very important and fundamental algorithms, because when you learn how linear regression works, many other algorithms later are based on linear regression. They're all built on top of linear regression. Of course, I'm not going to review linear regression in this class, but we had it last semester. But I want to tell you that why linear regression is so important, because the most advanced machine learning algorithms, like for example ANN, artificial neural networks, that we will cover this semester, and deep learning algorithms, they use the idea of linear regression. They are just adding some levels of feature engineering ahead of a linear regression, something like that. So it's a fundamental algorithm. If you use linear regression, this is a linear regression model that we learn from data. So this is the best fit to these training samples. So they're all training samples. Why? Because this is a house that was sold maybe last week in our neighborhood, and this was the size of the house, and this was the value of the house. So we know that the data, we know that the output, so it's supervised learning. And for now I have only one feature. In general I have 100 features, and this space will be can be n-dimensional. And so this line, so these are all historical or training data. This is the best line that I fit to all of these samples. And now when a new house, right here, this is a new house that we want to sell, we want to predict the value of that. So the size of the house is this in a square footage, and our model predicts this value in $1,000. So this is what we predict, okay? Your predictive model. So of course this data looks more like a quadratic model. So if we replace your linear regression with a polynomial regression, which is this blue line, a quadratic model, this is a better fit, right? And I talked about this last semester about polynomial regression. Probably if you use a regression problem for your project, I really encourage you to use polynomial, because, well, linear regression works in many cases, but there are not too many data sets in real life that has linear pattern. So this is again not too complex model. This is just quadratic, means it is order 2. So it means that this is my feature f, okay? I use a squared of this feature. Your model is quadratic. It is like using the squared of your feature in your model. So I want to tell you a very important trick in machine learning that we use in many cases when we want to use polynomial model. So in this case you have only one feature f, okay, one feature f right here, and the target, okay, your output. So your linear regression will be something like that. T that you want to predict is equal to, as you remember, for example, theta 0 plus theta 1 f, which is this feature, okay, right? So if you want to use a quadratic model, your model will be like that. Again, theta 0 plus theta 1 f plus this time theta 2 f squared, okay? So you want to use the squared of this feature to make this model quadratic or order 2, okay? So there are two different ways to do it. One technique is to use this model and train this model from scratch. So you think that you have 3 parameters and run whatever method you use, for example, gradient descent to find theta 0, theta 1, and theta 2 for this new model. Okay, so this is one technique. But a smarter way to do it, which is easy, it's a kind of trick in machine learning that we always use, is that define this fs squared as a new feature. So let me call this guy f1, okay, and let me call this fs squared as a new feature called f2. Okay, now your model will be something like that: theta 0 plus theta 1 f1 plus theta 2 f2. So it looks like a linear model with 2 features. Okay, so in fact I converted a non-linear model like this to a linear model by adding a feature. Now I can use the same rule as linear regression to train it, only with a new feature. So this makes everything much easier. Okay, so remember that. So this is a trick that you can apply, or you can train a non-linear regression, for example a quadratic regression model, by adding the squared of your feature as a new feature, and then train using linear regression. So I trained this model using linear regression now, but in fact the quadratic model, the s squared of this feature, is embedded inside this linear model. So this is a very smart way to make a non-linear model. All right, so with this non-linear model, of course, we make a better prediction because it's a better fit to my data. And as you see on this data set, the blue one fits better. Okay, this is training, this is feature table. Okay, and feature table includes your features. For supervised learning, as you see, we have features and we have label. So your feature table includes features and label, as many as features that you have. So this is the way you receive the data. This is the way you receive the training data. In this case, we have 4 features and 1 label. Our label has 3 different values, or 3 different classes: Setosa, versicolor, virginica, and 1 line of that is called a data sample, in this case training sample, and this part is called a feature vector. So the important thing is that always you receive the data in this format. Okay, and you work with this form, or if the data is not in this format, you have to convert it into this format to train your machine learning model. So in many cases, the data is not in this format. If you receive the data in the form of an audio signal, for example, but usually we extract features and create this table and then use it in machine learning. So this is our training data, and this is our testing data, or future data. So we receive these features and then predict something, the output that we would like to predict. So in prediction stage, we only have features. The problem of overfitting is an important topic that I want to talk about, and we will, again this semester, we'll talk about, especially in SVM and ensemble learning and artificial neural network. This is especially an important topic in artificial neural network when you make the network too complex and overfitting happens, and there are some techniques to your network simpler so that we can get better results. As you remember, overfitting happens when the predictive model, classification model, or regression model fits too much with the training samples, so that it starts capturing, learning, and representing the noise and randomness or outlier samples of the training data set. Remember that the data set has always include some bad samples, some wrong measurements, some bad data samples, and noise, a lot of noise. Especially if you, for example, collect data from a sensor, it may include a lot of bad data samples. So sometimes it's a bad sensor, for example, sometimes it's a wrong measurement, or sometimes users can generate wrong data, right? So if you, for example, go to your Gmail and mark the email of one of your friends by mistake or intentionally as a spam, okay, if you do it, for example, by mistake, then you created a bad data sample, right? But machine learning models should tolerate these bad data samples. How do we know that the model is overfitted? This is very important. How to diagnose that overfitting happened. When a model is in overfitting situation, it provides excellent accuracy for training data, but poor results for testing data or for future samples. So remember that. It still provides great results for training data. That's why it can be sometimes confusing. There are several reasons. The main two reasons for overfitting is when you have too many features, more than enough features. Some of them can be confusing, or some of them can be more than enough information that makes your model too confused, or force it to learn too much details that are unnecessary. Or when the complex model, when you use a very complex model with high order, so in this case features are not too many, but because your model is too complex, still it learns unnecessary part of the data, noise samples, for example. Okay, this is the example that I showed you last semester. There are three different cases: underfit, ideal fit, and overfit. So in this case, in the first one, as you see here, the data has a quadratic pattern, but we used a very simple model, linear pattern for the data. So this is called underfit or high bias. It's also high. Remember this keyword. The bias is high, the variance is low. I talked about this in 4661. And so in this case, we don't get good results because your model is too simple. This is ideal fit when we have a pretty good model for our data, but still, look, there are some errors here. These are some errors, but that's okay. Look at this model. Maybe error is 0 for this case because it passes through all of these samples, okay? So you get these, remember, these are training samples. So you get great results, excellent results on training, maybe error of 0, RMS is close to 0 for training data, okay? But this is a very bad model, of course, because for future, if we want to predict a value of the house for the house with this feature, for example, this is what it gives me, which is lower than this, okay? So it means that when the model is overfit, your model is bad. It gives you great results on the training data, but it gives you bad results for testing or future data. So look at this part is decreasing. So this is also called high variance or low bias. We have the same thing for classification, okay? In classification case, this is my data, and probably I can easily classify this data using this model, which is look like a quadratic classifier. Of course, if I want to use a linear model, it still works, but too many errors, so it gives me not great results. It still classifies most of the samples correctly, but accuracy is not high. This model is pretty good. I like it. As you see, still there are two samples here. Okay, two samples here that are either bad samples, wrong measurements, or they can be, they are not necessarily bad samples. They can be like difficult samples to classify based on only these two features. Okay, based only these two features, these two samples are not distinguishable with this model. So your machine learning model, in this case, well, I prefer a machine learning model that makes these two, that can tolerate these two errors, and instead it makes prediction very well for future samples. But look at this model. It gives me great results on training, okay, by excluding these two from the blue group. But it creates a very complex model for me. So this is overfit. That probably does not work well in future for future data. So overfit, high variance, low bias. Remember that. So as I mentioned, there are two main reasons for that. You have too many features or you have too complex model. To resolve the first problem, dimensional reduction or feature selection is the solution that I'm going to talk about this semester. Okay. You can manually select features. This is what you also did last semester for classifying iris flowers using KNN. You manually selected the best two features in one of your homeworks. But this semester I'm going to talk about some techniques for dimensional reduction. For example, for unsupervised dimensional reduction that squeezes your features and reduce the dimensionality of the data. So if this is your model with 20 features, you can make your model simpler and just keep 3 of them. Okay, maybe these 3 are the most important features. Maybe these 3 are the best features that include the information of most of the information of the whole 20. Or maybe you can get a very good prediction using only these 3, so you don't need the other 17. But how we can find these 3, or how we can squeeze, or how we can compress the information of all of our 20 features into only 3 features, we will talk about this later in this class. So you can manually do it on using some automated feature selection, dimensional reduction. All right, feature selection is an important step in machine learning. You should use it as a step before your machine learning algorithm this semester for your project. So for your project, remember, you should do feature selection and dimensional reduction before your machine learning algorithm, and I will talk about this. The classic feature selection algorithm usually focus on specific metrics to quantify the relevance and or redundancy of each feature. So we don't want a feature because it is not relevant or because it is redundant. Okay, so your feature selection algorithm should throw away unrelated features, useless features that does not provide any information, or repetitive features that provides the same information that other features provided. So we want to find the smallest subset of features that provides the maximum amount of useful information. So look, there are two optimization here: a smallest subset of features, or the minimum size with the maximum amount of information, and eliminate redundant or irrelevant, useless features. So maybe there is a feature that does not provide any information about the value of the house, so I don't want it. Or maybe there are some other features that I have another feature which is equivalent to that, so I don't want that too. Okay, so applying that will decrease the complexity of your system and improve the accuracy. We will talk about this. The other thing is to make your model simpler. So here, look, I have only 3 features in this model. Right here in this model I have only 3 features, but my model is too complex. I have s squared and I have order 3, one feature multiplied by the s squared of the other one. So your model is, although we only have x1, x2 and x3, so there are 3 features, but my model is too complex. So I make my model simpler, but by, for example, theta 6 equal to 0. So I remove this part and make theta 5 0 to get rid of this part. So my model will be a little bit simpler by removing some of these elements. And this is my new model. By doing that, you simply move from overfit situation to ideal fit, something like that. Okay, so remember, this is important. So by applying this technique, so for example regularization, you just move from this state to this one. You make your, I don't know, order 5 net model to like quadratic model, something like that. All right, regularization, I talked a lot about this last semester, and we will have it again. You know the idea, but we will apply it this semester for artificial neural networks, especially, and to make your network simpler and get rid of some of those connections and make your network more efficient. And later, when I talk about artificial neural network, you will see that our brain does the same thing. For example, for newborn baby, the brain is too complex. It is very, very complex network. It's a very complex machine learning model. And by time, the brain makes itself more efficient by making the network simpler and get rid of some of those connections. We will talk about this later in this class in deep learning.